Okay, so today what we're going to do is take a look at the last segment of our unit, which is homeostasis. So at this point what we've done is we've actually talked about the structure of the cell membrane, kind of revisited why the cell is what we call that package of living material. We've also looked in very much detail at the cell membrane. We've also looked at the different transport mechanisms, both active as well as passive, that can exist. And we've also looked at the internal transport systems, both within a cell, through the endoplasmic reticulum and the Golgi apparatus, and also how things are transported within multicellular organisms. All of these things that we have discussed are the primary regulators of a condition called homeostasis. And I know you've heard that word before, so we're going to actually kind of take a little closer look at homeostasis, look at some specific examples that are typically used, so that way when you take the Keystone exam, if they use some of these examples, you know what they're trying to get you to think about is homeostasis. A lot of times they will use some of these examples in their questions, and it's not that you need to know anything about the system, but you need to be able to generalize and understand that it's talking about homeostasis. So on your notes you see this kind of half of a graph grid structure. Okay, so this part here, the horizontal dash line, is your x-axis, and then you've got your vertical y-axis there. If we were to plot something along there, that x-axis, that horizontal steady line, represents homeostasis. Now we are going to be writing some other things on there, so just so you know, I'm putting things up here very big, simply because that way then you guys can see it. So this line here, the dashed horizontal line, represents homeostasis. Homeostasis we need to think of as the ideal state. In other words, everything is running exactly the way that it should, and in this particular instance, for whatever specific thing we are looking at, therefore we are maintaining that very stable internal state. Now, homeostasis, though, very rarely exists. If we were to actually look at what happens, if we were to actually kind of plot the state, let's say we were looking at something like body temperature. Okay, we would start with our body temperature here in the morning, which is actually kind of around normal. Let's just say right here. Okay, it's about normal. And as we go through some of our activities through the day, it slowly increases up to here, as you can see. Now, there are certain things that we do throughout our day that actually causes our body temperature to drop. One of them is eating. So when we eat, we actually put more energy into the digestion of food than we do into maintaining our body temperature. So as you can see here, the body temperature starts to drop, and eventually it reaches a low point. And this would be when our body's thermostat kind of kicks on and goes, oh, wait a minute, whoa, we're a little too low. We need to kind of kick on the heat and bring it back up. The heating systems in our homes work very much the same way. The heat comes on, we get to a high point, the thermostat shuts off, the temperature drifts down a bit, and then it triggers the thermostat to kick back on, the heat comes back on. Now, in terms of what you guys should draw, I only drew one portion of the curve. It actually looks a little bit more like this, okay, with this waviness. Okay, and notice that it maintains a very tight area right around homeostasis. So in going through this, I hit homeostasis here. Let me get a better color. Here, 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 here. So there are points in this where we do achieve homeostasis. We don't stay there very long, but at the same time, we always kind of bring it back towards that homeostasis. If we get a little too high, we come back down. If we get a little too low, we bring it back up. Okay, this is the state of what we call dynamic equilibrium. And this is the reality of how our bodies actually maintain themselves. It is very, very difficult for whether it's a cell or whether it's a multicellular organism like us to maintain that very steady state over a long period of time. So what happens is, in reality, we actually have this oscillation, this going back and forth around homeostasis that is dynamic equilibrium. Now, we regulate this by our organ systems in the body. Now, every so often, we would go through an increase. Let's just say we have an increase here. Let me get my pen working again. Okay, let's say we start here with our body temperature and it starts to go up, but at this point, instead of dropping down, it continues to go up. Okay, that's a problem. We actually don't function very well, and as we've talked about, our enzymes start to denature when we get to too high of a body temperature. This would be like the area we would call a fever, and if we did the opposite, if we started dropping down too low, we would get what's called hypothermia. So not turning it back around and coming back towards homeostasis is a problem. Now, I use body temperature as an example simply because it's something you're familiar with. In general, though, if homeostasis fails in an organism, we generally say that that organism ends up with a disease. Getting sick or getting a disease, whether it's cancer or any illness, the cold, the flu, is a result of a disturbance in the homeostasis of that organism. If homeostasis fails and we get a disease or an illness, what typically happens is if we do nothing, the symptoms of the disease are going to progress. In other words, those symptoms are going to continue to get worse and worse over time unless something is done. If that happens, organism death can actually occur. And you do see that with body temperature. If you have a very high sustained fever for a long period of time, you can actually die just from that. Same thing with too low of a body temperature. You can actually die from just that. So, how do organisms and even us in particular maintain homeostasis? We maintain homeostasis through mechanisms that are called feedback mechanisms. Basically, feedback mechanisms give information back to the organism that tell them how to adjust things. A single cellular organism living in fresh water will have a feedback mechanism that tells it when to turn on and turn off the water pump that helps to pump water out of the cell so that it doesn't burst. We have these in us as well. The most common mechanism that we see is something called negative feedback. Negative feedback is basically where the body or the organism produces a response that is aimed at reversing what has just happened. The less common one is something called positive feedback, and positive feedback actually happens with you generate a response that increases in intensity, so it increases positively until the disturbance is corrected. Both of these, though, are very important. It just depends on how the disturbance occurs. So we're going to take some time here and really look at negative feedback, simply because that is the most common form of maintaining homeostasis. So like I said, negative feedback corrects the disturbance in homeostasis by creating a change that does the opposite. So it's easy to talk about using some of our classic examples, which include body temperature, pH, your blood sugar levels, hormone levels, oxygen levels, electrolyte levels, or even water levels. If any of these get too high, your body produces a response to decrease it. If any of them get too low, your body creates a change to increase it. So what we're going to do is we're going to go through 4 examples. We're going to go through the body temperature, we're going to do blood sugar, we're going to do the water levels, and we're going to do the pH. Alright, so you see these diagrams, you have 4 of them, and what we're going to be doing is we're going to be filling them in. The first negative feedback example we're going to look at is our body temperature. And the disturbance that we're going to generate first is that the body temperature increases. So let's say we're working out, our body temperature increases, okay? That triggers a change in our brain. The brain actually opens up the blood vessels at the skin and also triggers our sweat glands to release sweat. This actually helps to transport heat from the center of our body to the outside and then let it dissipate into our surroundings. Now, as that happens, our body temperature is going to decrease. Now, if our body temperature decreases too much, let's say we go from being in a very warm environment where we need to release heat to a cooler environment where we don't want to release heat, and our body temperature drops too low, then the brain is going to close the blood vessels and start our process of shivering, because those muscle contractions will actually help to keep us warm. Okay, the second example we want to look at is our blood sugar level. After we eat, our blood sugar level actually increases because we're we're digesting down the carbohydrates into glucose, and that glucose goes into the bloodstream. This triggers our pancreas to secrete a hormone that I know you guys have heard of, which is insulin. Insulin causes the glucose to get stored in our cells. It's basically the signal to our cells that, hey, you guys need to take out some of this glucose from the blood. Now, a little while after we have eaten, once that digestive process has stopped, we're no longer adding blood sugar to our blood, and we can actually reach a period where we actually have low blood sugar. Okay, whether it's because of the glucose getting stored or the time since we last ate. The pancreas, a different set of cells in the pancreas, will then release a different hormone called glucagon. And what this triggers is the glucose to get released from its storage area. The third mechanism of homeostasis or negative feedback is going to be our water. If we look, the biggest area that we have water is in our blood, and our blood is actually what we monitor a lot. I mean, you saw blood glucose, how we monitor body temperature is in the bloodstream, just because it travels to all areas of our body. So we actually have a mechanism by which we look at the water levels. If our water levels are high in our blood, it is actually detected by our kidneys. And our kidneys, in addition to our skin, work together to get rid of excess water. And we've all had that. We have a lot to drink, and what do we have to do? We have to go to the bathroom. Now, as we get rid of that excess water, sometimes we reach a period where maybe we're not bringing in as much water into our bodies, so the water levels can actually drop inside of our blood. What this means is our kidneys will actually work to return more water into our blood after it has filtered the blood. And again, that can increase the water level, and if we are intaking more water then it can cycle back. And you can see how all of this is a cycle that actually repeats itself. And that's what gets the up and down oscillations that we saw in dynamic equilibrium. All right, the last one that I want to look at is pH levels, especially since we talked about pH pretty recently. Again, we're going to monitor this in the blood because the pH of the blood is reflecting what's going on in our different tissues. Okay, first of all, our blood pH levels will drop. If they go down low, that means, remember, that it's an acid. Now, an interesting change that happens actually affects our breathing. We actually breathe faster when our blood pH level has dropped, and our kidneys also release a base. Remember, acids and bases neutralize each other. So by releasing a base, we'll actually bring that blood pH back up to the levels that it needs to be. Now, after a little while, we may actually end up with blood pH levels too high. Our blood pH level tends to be right around 7. It's a little bit on the basic side, but when we're saying that the pH levels rise, we're saying it's too far into the basic side. So when this happens, we actually decrease our breathing rate, and our kidneys are able to release a different compound. Now they're able to release an acid to help lower the blood pH. And again, you can see that this it creates that cycling that we talked about, that up and down. Let's see if I can draw it here. That up and down type of thing that we talked about around the level of homeostasis. Okay? All right, so that kind of talks about homeostasis and our homeostatic mechanisms. So this actually completes our look and our introduction of new material for the unit.